nice and fun. We had fun putting it together. I have Nishi and Kiara with me. Let's go. Tap. Clap, clap. Open. Good. All right, we're going to keep the hands the same. We're going to change the feet. Take it out. 4. Good, good. Open. All right, we're going to have us change here. Rock.
So, hi everyone! I hope we are all energized by our little performance we have prepared for you. So, we will discuss about science, matter, energy, and systems. But before that, we will have the objectives for these discussions. And these are, we will be able to know what the scientists do. Second, we will be able to know what is matter and what happens when it undergoes change. So, general process that scientists use for discovering and testing ideas. So, let me discuss first about science. I know that we have encountered this during our grade school, and I will just recap this. Science is a broad field of study focused on discovering how nature works and using that knowledge to describe what likely to happen in nature. According to Henry Poincaré, science is built of facts as a house built of stones, but an accumulation of facts is no more a science. That heap of stones is a house. So, science is a pursuit and application of knowledge and understanding of the natural and social world following a systematical methodology based on evidence. Next. What do scientists do? What do really scientists do? Okay, so scientists they collect data, develop hypotheses, theories, and laws about how nature works. Second, scientists, they observe, they experiment, and they make models to the answers they have gathered about how nature works. And lastly, scientists, they are most likely curious and skeptical, and they demand evidence. So, scientist is someone who is systematically gathers and use research and evidence to make hypotheses and test them to gain and share understanding and knowledge. So, furthermore, scientists, these are the people who discovers new things and research how things work. There are many different types of scientists. Actually, they observe, measure, and communicate results to people like you and me. So basically, they make an observation, they ask questions, gather information, creates a hypothesis, and then they test their hypothesis if it is accepted or not, and the data and replicating the test until the observations and theory aligns. So that's what a scientist means. So next, as we can see in the presentation, is like a structure. So this structure is by Borman and Likens core case study, wherein it shows the general process that they use for discovering and testing ideas about how natural world works. So first step is they identify the problem. Second, they find out what is known about the problem or the literature. Second, they ask questions to be investigated. Next, they perform an experiment to answer the questions, and they collect data. Third, they analyze data or they check the patterns if it is scientific law or a well-accepted pattern in data. Next is they propose hypotheses to explain the data. Third, use hypotheses to make testable projections. And perform an experiment to test projections. So if it is accepted, if your hypothesis is accepted, you can make a scientific theory it is a well-tested and widely accepted hypothesis. So if your hypothesis is not accepted, you can still revise it. You make testable projections, and next is test projections, and by that your hypothesis will be accepted and you can create a scientific theory. So in this structure, Marjorie, my other groupmate will discuss more. Will give an example to this theory to give us more ideas and clarifications regarding this.
Thank you, Donna. Now, I will proceed to our example. We use figure 2, the scientific process, to understand and deal with everyday problem. We use an flashlight. For observation, nothing happens when I try to turn on my flashlight. And here comes our question. Why didn't the light come on? Maybe, and we try a new hypothesis. Maybe the batteries are dead. Then, to try or to test our hypothesis if it works, we go and experiment about that. We put new batteries and try to turn on the flashlight. As a result, the flashlight still does not work. And then we try another new hypothesis. Maybe the bulb is worn out. And experiment again, we will put a new bulb. As a result, the flashlight will work. And then that's our conclusion. The new hypothesis is verified. Now, let's move on. Critical thinking and creativity that are important in science. Thinking critically involves the 4 important steps. First, be skeptical about everything you read and hear. We can never entirely for granted, or we can never take entirely for granted the absolute trustworthiness and what we read or see or hear from the media or of any kind. This is the case for information from traditionally news organizations, blogs, online videos, and other form. Second, look at the evidence and evaluate it and any related information along with inputs and opinions from a variety of reliable resources or sources. Second is validating information, especially. It is important in the internet age where we can be exposed to unreliable data, some of which may be just opinions from uninformed amateurs posing as an expert. And third, be open to many viewpoints and evaluate each one before coming to a conclusion. Of course, we should listen to other people. We should listen to other opinions before we conduct our conclusion. And the fourth and the last, identify and evaluate your personal assumptions, biases, and beliefs, being careful to distinguish between facts and opinions. So, logic and critical thinking are very important tools in science, but imagination, creativity, and intuition are just as vital. According to physicist Albert Einstein, there is no completely logical way to a new scientific idea. Most major scientific advances are made by creative people who came up with a new and better ways to help us to understand how the natural world works. Scientific theories and laws are the most important and certain results of science. Facts and data are essential to science, but its real goal is to develop theories and laws based on facts that explain how the physical world works. First, we should never take a scientific theory lightly. It has been tested widely, it is supported by extensive evidence, and is accepted as being useful explanation of some phenomenon. Most scientists is in a particular field or of related field of study. Because of this rigorous testing process, scientific theories are rarely overturned unless new evidence This credits them or scientists came up with better explanations. So when you hear someone say, "Oh, that's just a theory," you will know that he or she does not have a clear understanding of what scientific theory is, how important it is, and how rigorously it has been tested before reaching this level of acceptance. Second, another important and reliable outcome of science is a scientific law or the law of nature, a well-tested and widely accepted description of what we find happening repeatedly in a nature in the same way.
So I'm back again and again and again and again. So the next is the result of science. It can be identified if it is reliable, unreliable, or tentative. A fundamental part of science is testing. Scientists insist on testing their hypotheses, models, methods, and results over and over again. In this way, they seek to establish the reliability of the scientific tools and resulting conclusions that they reveal about how part of the physical world works. So, reliable source, science, reliable science. It is consists of data, hypotheses, models, theories, and laws that are widely accepted by all or most of the scientists. Sometimes, preliminary scientific results that capture news headlines like we see in television are controversial because they have not been widely tested and accepted by peer review. They do not undergo process. They are not yet considered reliable and can be thought of as a tentative or frontier science. Some of these results will be validated and classified as reliable, and some will be discredited and classified as unreliable. At the frontier stage, it is normal for scientists to disagree about the meaning and accuracy of data and the validity of hypotheses and results. This is how scientific knowledge advances. Hypotheses, models, theories, and laws that are widely accepted by all of the most scientists who are considered experts in the field under study is what is referred to as scientific consensus. The result of reliable science is based on the self-correcting process of testing, open peer review, reproducibility, and debate. Next is the unreliable science. It is the scientific hypothesis and result that are presented as reliable without having undergone the rigors of peer review, or that have been discarded as a result of peer review or additional research. So, scientific hypotheses and results that are presented as reliable without having undergone the rigors of wider spread peer review or that have been discarded as a result of peer review are considered to be unreliable science. Lastly is the tentative science. Preliminary scientific results that have not been widely tested and accepted by peer review or tested and reproduced by other scientists are not yet considered to be reliable, but a tentative science or a frontier science. Sometimes, preliminary scientific results that capture news headlines are controversial because they have not been widely accepted by a peer review. So they are not yet considered reliable and can be taught as tentative or frontier science. So those are the results that can be identified if it is reliable, unreliable, or tentative.
The last discussion of this lesson, science has some limitation. Environment science and science in general have 5 important limitations. First, Scientists cannot prove or disprove anything absolutely because there is always some degree of uncertainty in scientific measures, observation, and models. A second limitation of science is that scientists are humans and thus are not totally free of bias about their own result and hypothesis. However, the high standard of evidence required through peer review usually uncovered or greatly reduce personal bias and expose occasional cheating by scientists who falsify their result. A third limitation, especially important to environment science, is that many systems in the world involve a huge number of variables with complex interaction. This makes it too difficult and too costly to one variable at a time is controlled experiments such as the one described in the core study that opened this chapter. Fourth and lastly, limitation of science involve the use of statistic tools. For example, there is no way to measure accurately how many metric soil are eroded annually worldwide. Instead, scientists use statistical sampling and other mathematical methods to estimate such number. That will be all. The next topic will be discussed by the next reporter.
Next topic is matter and what happens when it undergoes change. And before that, let me give you a brief meaning about matter. A matter is consists of elements and compounds that made up of atoms, ions, and molecules. Matter is anything that occupies space and has a mass, and it consists of three physical states, which is solid, liquid, and gas. First, solid. Solid is characterized by structured and resistant to force applied to surface. Second, liquid. Liquid is a state of matter, intermediate phase between solid and gas. Third, gas. Gas is a state of matter that has no shape and volume. And then, matter has a two chemical forms, which is elements and compound. The two chemical forms of matter, which is elements and compound, will be discussed by the next reporter.
Let's proceed now to the two chemical forms of matter, the element and the compound. Element is the fundamental type of matter that has set of properties and cannot be broken down into substance by any chemical means, while compound is a combination of two or more elements held together in a fixed proportion. So we have this also the building blocks of matter. The basic building blocks of matter is an atom, the second building blocks of matter is a molecule, and the third building blocks of matter is an ion. Atom is the smallest unit of matter and has a unique structure when you use a microscope. We can see there the three subatomic particles, neutrons, protons, and electrons. Neutrons has no electric charges, protons has a positive electric charges, and electrons has a negative electric charges. Each atom consists of extremely small center called the nucleus. Nucleus contains one or more protons, in most cases, one or more neutrons, and one or more electrons in rapid motion somewhere around the nucleus. Let's proceed now to the second building blocks of matter, which is the molecule. Molecule is the combination of two or more atoms at the same or different elements held together by forces called chemical bonds. Molecules are the basic building blocks of many compounds. Example of molecules are water or H2O, which consists of two atoms, the hydrogen and the oxygen, which is held together by chemical bonds. So let's proceed to the third building blocks of matter, which is the ion. Ion is an atom or a group of atoms with one or more net or negative electric charges. Like atoms, ions are made up of protons, neutrons, and electrons. A positive ion forms when an atom loses or one or more of its negatively charged electrons, and a negative ion forms when an atom gains one or more negatively charged electrons.
Let's proceed to the organic compounds are the chemicals of life. Organic compounds or the chemical compounds of living things are also known as organic compounds because of their association with organisms, and also they are carbon-containing compounds. Organic compounds, which are the compounds associated with life processes, are the subject matter or organic chemistry. The importance of organic compounds are because living organism contains carbon. Under this, there are three basic micromolecules of life are carbohydrates, fats, and proteins. Several types of larger and more complex organic compounds essential to life are called polymers. They form when a number of simple organic molecules or monomers are linked together by chemical bonds. Under this, there are three major types of organic polymers, namely complex carbohydrates, proteins, and nucleic acid. Complex carbohydrates such as cellulose and starch. Proteins formed by monomers called amino acids, and nucleic acids formed by monomers called nucleotides. Matter comes to life through cells, genes, and chromosomes. Cells are the fundamental structure and functional units of life. Cell theory, the idea that all living things are composed of cells. Genes, certain sequences of nucleotides. Genetic information, distinct pieces of DNA that contains instructions or codes. In turn, thousands of genes make up a single chromosome, a double helix DNA molecule wrapped around one or more proteins. Genetic information coded in your chromosomal DNA in what makes you different from an oak leaf, alligator, and mosquito, and from your parents.
As a continuation of the group report, my topic is all about matter undergoes physical, chemical, and nuclear changes. So when a sample of matter undergoes a physical change, there is no change in its chemical composition. Just like, for example, a piece of aluminum foil cut into small pieces. The small pieces of an aluminum foil is still an aluminum foil. And also, with the composition of a solid water or ice, When an ice melts and when liquid water boils, the resulting liquid water and water vapor are still made up of H2O molecules. The chemical reaction or chemical change takes place. There is a change in the chemical composition of the substance involved. Chemists use a chemical equation to show how chemicals are arranged in a chemical reaction. For example, coal is made up of almost entirely of the element carbon. When coal is burned completely in a power plant, the solid carbon in the coal combines with the oxygen gas from the atmosphere to form the gaseous compound carbon dioxide. The chemical reaction or chemical change takes place. There is a change in the chemical composition of the substance involved. Chemists use a chemical equation to show how chemicals are arranged in a chemical reaction. For example, coal is made up of almost entirely of the element carbon. When coal is burned completely in a power plant, the solid carbon in the coal combines with the oxygen gas from the atmosphere to form the gaseous compound carbon dioxide. In addition to physical and chemical changes, matter can undergo three types of nuclear change or change in the nuclei of its atoms. These are the radioactive decay, nuclear fission, and nuclear fusion, which are described and defined in the preceding topics. A radioactive decay occurs when nuclei of unstable isotopes spontaneously emit fast-moving chunk of matter, or the alpha particles or beta particles, and the high-energy radiation, or the gamma rays, and both at a fixed rate. Next is the nuclear fission. A nuclear fission occurs when the nuclei of certain isotopes with large mass numbers, such as the uranium-235, are split apart into lighter nuclear when struck by a neutron and release energy plus 2 of 3 more neutrons. Each neutron can trigger an additional fission reaction and lead to a chain reaction, which releases an enormous amount of energy very quickly. Next is the nuclear fusion. The nuclear fusion occurs when two isotopes of light elements, such as hydrogen, are forced together at extremely high temperatures until they fuse to form a heavier nucleus and release a tremendous amount of energy. So the next topic will be, for the information of everyone, we cannot create or destroy atoms. This was supported by the law of conservation of matter. This states that we can change elements and compounds from one physical or chemical form to another, but we can never create or destroy any of the atoms involved in any physical or chemical change. All we can do is rearrange the atoms, ions, or molecules into different spatial patterns or physical changes, or chemical combinations or chemical changes. These facts, based on many thousands of measurements, describe a scientific law known as the law of conservation of matter. Whenever matter undergoes a physical or chemical change, no atoms are created or destroyed. That's all. Thank you.
That's it for our topic for today. So to wrap up everything, we discussed about what do scientists do and
Matter and what happens when it undergoes change.
so please don't forget to like,
Share, subscribe, and click the notification bell.
For more updates,
And more upcoming videos.
Please comment your questions and suggestions in the comment box.
Thank you! God bless and stay safe from Group 1!